So this is just to finish up on the chapter on radioactivity. So we want to look at the Geiger Muller tube. Now there's two types of detectors, radiation detectors you need to know if you're leaving cert. The Geiger Muller tube or the solid state detector. Sorry, I should say it's sufficient to know one of them. And the most popular one is the Geiger Muller tube. It's on page 58 in your textbook. As a starting point, though, I'd probably look at Noel Cunningham's, the physics teacher guy's explanation of the GM tube there, which I'll put up in Edmodo, the file. You can have a look at that. It starts at 13 minutes and 18 seconds into the video. This whole section is fascinating stuff. I would highly recommend also you have a quick read through maybe chapter 30 on the Word document in the physicsteacher.ie on this section. So anyway, the Geiger Muller tube. So essentially what happens is you have some radioactive source and it passes into the GM tube. Now what is the GM tube composed of? Well, you've got a rate meter which counts the number of pulses coming from the GM tube. The GM tube itself has an anode at the center, cathode on the outside, and a thin mica window. You can look up mica. It's used in makeup and all sorts of applications, if you like, MICA. But it's basically, in this case here, you can make a very thin layer of it and it will still hold its shape and stop the gas in the GM tube from escaping. In a GM tube, the gas actually is argon gas. So what happens is a radioactive source like an alpha particle passes through the thin mica window, crashes into the argon atoms and ionizes them, which essentially means it knocks the electrons off them. Thus you have positive ions and electrons, and the electrons that are knocked off the atoms will charge towards the anode, which is at a very high voltage, typically 400 volts. And on the way, they ionize further argon atoms. So you end up with an avalanche of atoms, and that causes a pulse of electricity, which gets amplified, and then it's given out as a pulse. And that's essentially how the Geiger Muller tube operates. Now, just skipping on to radioisotopes. So the other thing when we deal with in this chapter is radioisotopes. The vast majority of them these days are produced in nuclear reactors. Now, inside nuclear reactors, there's neutrons basically flying around. We discuss this in much more detail in the next chapter. So what you do is you place your material, typically like something like cobalt-59, inside a nuclear reactor, and some of that cobalt-59 will absorb a neutron into its nucleus and become cobalt-60, and thus becomes radioactive. And it actually becomes a gamma ray emitter, and it has various uses like for sterilizing surgical instruments, cancer treatment, food irradiation. Another example is americium-241, using smoke detectors and also for measuring thickness in things like maybe tin foil and steel and paper production. Another example would be carbon dating, used to measure the age of something. So if you had a dead plant or animal from thousands of years ago, when it dies, it doesn't take in any more carbon. And every person or every living thing and every piece of natural material has a certain amount of carbon-14 in it. And over time, the amount of carbon-14 will decrease. So therefore, if you measure its activity, you can estimate its age. Now, the mole is mentioned in your book, but it's not mentioned in the syllabus, and I've never seen an exam paper, so I'm not going to discuss it here. So a few other little bits and pieces there. Some guy has gone to the trouble of making an hour-long video on the sound of a Geiger counter. That's that familiar kind of scratchy sound. That is a sound a Geiger counter would make. Just to look at the Geiger counter in action here, nice little GIF here of it. So the radioactivity comes flying in through the mica window, and it crashes into an argon atom. It ionizes, and on the way over, the electron causes further ionization, and you get your avalanche of electrons and the pulse, which goes to the rate meter to be counted. And that is pretty much it, I hope.